So, good afternoon, everybody. Welcome back to this afternoon session of the SPIN Symposium. It's my big pleasure to introduce the SPIN invited speaker, Shaz Qadeer. Shaz holds a PhD from UC Berkeley and has been since 2003 a senior researcher at Microsoft Research in Redmond. His mantra is to make programming easier and to simplify the construction of concurrent programs, and he is going to talk to us about the P system that he's currently working on. Shaz, please.
Thank you, sir. Thank you, Stefan. It's a great honor to be here. I'm going to tell you about the P programming language that I've been working on with colleagues at MSR and also at some universities for the past 3 years. So until about a few years ago, Microsoft was a company that was known for its operating system and for the Office suite of software, which is basically shrink-wrap software. That's not true anymore. As with a lot of other companies in the computing industry, Microsoft is heavily betting on devices and services. So services that are running in the cloud and lots of devices that are accessing those services using phones and laptops and all sorts of other devices that are all pulled together under the rubric of IoT or Internet of Things. So that's a big motivation of the work that I'll present. You'll see that the problems that P tries to address, the programming language P tries to address, are very classical problems. But I think those classical problems are seeing there's a renewed urgency behind trying to solve those problems because of this particular explosion or change in the computing industry. So device drivers are the low-level software that is used to run devices. And cloud services, they're complicated. And they're complicated for a variety of reasons, but the focus of this talk is on concurrency and reactivity. So concurrency means that there are multiple processes that are interacting with each other. And as you can imagine, this is the norm, right? So if you have a device driver, you will have some piece of software interacting with the hardware. That piece of software itself could have been constructed as a composition of multiple processes talking to each other. Reactivity simply means that this is performance critical, so you can't just afford to queue all incoming requests until existing work has finished. So oftentimes, software is forced to accept requests even when there is pending work. And that creates complication, a complication that is not dealt with in typical sequential programs. Another complication that these kinds of programs have to deal with is failures. So a request that is sent out to a service that I'm talking to may not get a response to it. So you have to deal with the timeouts to say, okay, when can I give up on this and try something else? So requests may fail. In a distributed system, messages may be dropped by the underlying network, or an entire computing node might disappear. The service must continue to operate. It's not acceptable to stop the programs just because an individual request or an individual component fails. So these kinds of problems further add to the concurrency and reactivity challenge. A big problem that happens in this kind of software because of these challenges is the problem of Heisenbugs. So I use the word Heisenbug to refer to a bug that happens because of rare interactions between concurrently executing components and rare failures. This may not happen in the normal course of events, but it will happen once in a blue moon, and it will cause the system to crash. A disturbing aspect of this kind of bug is the lack of reproducibility. So the reason it's called a Heisenbug, it's a pun on Heisenberg's uncertainty principle, where if you try to observe the system, the behavior of the system changes. So reproducing these failures is very difficult, because if you try to observe the system by logging or by setting breakpoints, etc., it causes the bug to disappear. It's as if the bug automatically got fixed, but of course not. It's because it caused a change, a perturbation to the system, a different schedule happened, and that does not cause the bug to manifest itself. So this is a huge, huge, huge problem for programmers. I'll give you an illustration of how these kind of problems manifest themselves in building these kind of services. So my example is in the context of the Azure storage service. vNext, I call it vNext because it's the next generation that is being built by collaboration between some Microsoft researchers and product groups. So here there is this idea that a unit of data is called extent in the parlance of this service, right? So there's lots of extents. So the whole universe of extents is partitioned among a whole bunch of extent managers. So each extent manager deals with a subset of extents, and the storage for those extents is being dealt with by these so-called extent nodes, right? Now, because to deal with failures, we want to continue to provide access to the data, so each extent is replicated across several extent nodes, okay? So in the presence of failures, we got to make sure that a certain number of replicas are always maintained. That's a requirement of the protocol. So this is what happened. So the software developer wrote a whole bunch of unit tests, and each unit test verified the behavior of the extent manager in isolation, and they all passed. Very good. Then he also very diligently did integration tests. So he launched the real extent manager and extent nodes, kills one extent node, launches another one, makes sure that the extent is repaired, and that also worked. So this is all great. But where happiness dies is in this situation, where there are these stress tests. Now you're operating things at scale. So you have lots of extents, lots of extent nodes, and you are just killing them and bringing them up all the time. So every once in a while, what the programmer notices is that the repair gets stuck. Now by the time this problem is noticed, the logs that have accumulated on the different nodes will run into hundreds of thousands. And now it's very hard to figure out why this problem is happening. And of course, it has all the other issues with Heisenbugs, that it's very difficult to reproduce this. So if you try to do something else, you may not see the problem. This is very common. This is the example that I gave you was Microsoft service. But if you look at the bug databases of open source software systems, there's lots of similar examples there. So the goal of the P programming system is to offer a possible solution to the Heisenbug problem. So our goal is to find and fix Heisenbugs during development and testing, so that these bugs don't leak into production when the service is in production. So here's a picture explaining P. By the way, it's perfectly okay to have questions in the middle of the talk. We don't have to hold off until the end of the talk to ask questions. Okay, so this picture here shows you the typical workflow used by the P programmer. So on the left side is a P program. So the P program is a repository of everything about the code. It's the code, it's the models, the specifications, and unit tests. So it's interesting. So one thing that is very interesting is that code and models reside together. So what are these models for? Well, code is the code of the service that's going to run. You're going to run it through the compiler, generate executable code. But a lot of these Heisenbugs happen because of interaction between the code and its environment. The environment could be like the network stack, for example, or in the environment, a node is failing. Well, that's not code. You have to somehow model it, right? So in P, the entire programming language is available both for expressing code and for models. There's no difference between the language constructs that are used for coding and the ones that are used for modeling. Then we have specifications. Well, specifications we all sort of understand. There will be safety and liveness specifications. They are the principal mechanisms by which debugging is done. You write specifications. When they fail, then you get an error trace and you debug your way back. The more specifications you can write, the better your debugging is going to be. Another very important thing about P is that we have tests here. Now these tests are what I call concurrency unit tests. So unlike standard unit tests in which you just generate one execution, these are unit tests in which there is non-determinism. And that non-determinism, because the P compiler understands all the sources of non-determinism, they get captured. And we generate these concurrency unit tests with controllable non-determinism. And now those sources of non-determinism can be enumerated algorithmically by this systematic concurrency testing tool that we have developed for P. Okay? When it produces an error trace, it would be reproducible because we know and control all the sources of non-determinism. So there's this loop here where the programmer will fix things here appropriately, and ultimately when he's satisfied with the quality of the code, he runs the same P compiler, and asks it to emit executable code. So what is very important is that the same code that was being tested over here is the code that is going to be executed here. So here you see how that code gets deployed. So the output of the P compiler will generate, say, a C file, right? This is the auto-generated thing. You're not supposed to edit this. You're supposed to edit only the stuff over here. But the entire application, the entire service is going to be built not just from the P code, but also with some handwritten code. That is inevitable because there will be some amount of code that will be interacting with the rest of the services that comprise your application, right? So that would be handwritten code, and that would link together with the P runtime library and the operating system and so on, and that forms the application execution. Okay, so a few comments about modeling versus programming. So some of the stuff that I said in the previous slide might seem familiar to you because this is a conference devoted to model checking. So modeling is something that we all know. In fact, there are many modeling languages that have the research that our community has produced over the years. Some of the most noteworthy from the point of view of asynchrony and concurrency, I note up there TLA+, Spin, Murphy. So one characteristic of modeling languages is that they were always supposed to be different from programming languages. There was a gap between the model and the code, and this connection was informal and typically unchecked. And in my mind, that is one of the biggest impediments to the adoption of modeling by real software engineers. Because even if they did modeling, eventually they have to write executable code, and then any bug fixes or any feature additions happen over there. So they don't like to have two separate representations because now they have to maintain it. And even if they were trying to maintain it, they wouldn't know whether the two match each other. So that's the problem that P really tries to solve here. P is both a modeling and a programming language. And it basically erases the difference between modeling and programming and eliminates this problem. So it's much easier to explain why this is useful to programmers. Okay, so we've been working on P for about 3 years now, and we have gotten some experience getting it used to solve real programming problems. An early use case of P was in developing the USB device drivers that ship with Windows 8.1 and subsequently with Windows Phone. So these are very complicated drivers with lots of asynchrony. They're built as an interaction of concurrently executing state machines and so on. From my point of view, the most interesting aspect of this particular case study was that hundreds of bugs were found and fixed before a single line of C code was started executing on the real devices. That's one. And the second thing is, of course, what I said earlier. there was no distinction between modeling and programming. The code that was validated like that was run through the compiler, and it generated the C code that was running inside the driver. More recently, HoloLens development got underway. Some of the engineers from Windows moved over there, and so they heard about P. They used that to model a low-level DMA driver, and that was helpful to them. We are currently trying to heavily engage with Azure, and they're trying out P to implement cloud services. Not distributed protocols, implementation of distributed protocols, but really cloud services. And the code that they're writing is kind of similar to device driver code, heavily concurrent, but single node code. A couple other things that have happened in the last few years is the emergence of library extensions to mainstream programming languages that are based on the model of computation that P espouses. So there's a programming language called Psharp. It's an extension to C#. So unlike P, which has its own syntax, right, and therefore the application is written in P and in C, and to interact between the two, the programmer has to deal with an explicit foreign code interface. In Psharp, you can just use C# code naturally inside the Psharp language. So you don't program with an explicit foreign code interface. So that part is really nice. The part that is not so nice is that you have to deal with all of C#, which is at this point, a massive framework. Another nice aspect of Psharp is that it's not just about writing new code. You can even use Psharp to find and reproduce Heisenbugs in existing code services that are written in C#. By basically using Psharp as the P concepts for doing the environment modeling, and using those environment models to drive the C# code. So the bug that I was showing you earlier in Azure Storage vNext, that bug was found and fixed for the first time using Psharp. Turns out that it was the way it was fixed was that you wrote a liveness property. There's a liveness specification, and the violation of that led to the violation of that liveness specification gave you the root cause behind the bug. So Psharp is also gradually seeing adoption inside Azure, and there are other approaches like Psharp that are being used to test services that are written in C or C++. Here's another interesting thing. It's called P++. This is like Psharp, but it's a library extension to C++. From my point of view, this was very interesting because I was not involved in this. Engineers inside Office and Azure, because P is open source, and they must have heard about P from some talk, and they just went ahead and implemented P as a library extension to C++. But they are sticking to the language features and their semantics. So that's nice. So there's conformity there. And they have some primitive support for specification modeling and systematic testing, though not quite as good as for P and Psharp. So now I want to give you a yeah.
Quick question. So in all of these applications, like you were saying, you have to write an environment model. And I guess you have to write fairly complicated ones. Was that the case for these applications? And do you see that these environment models can be reused?
Yeah, I think so. So sometimes they get complicated. One question that often comes up is that I'm writing this model. It's supposed to, capture what is going on in this thing. How do I know that I got it right? That's one question. And then the other question is that of reuse. So I think that reuse question is easier to answer. So if, for example, if you're modeling the network layer, if the same kind of network layer is I can imagine that the network layer would be the same for many product groups inside Azure, and you can now reuse it. The other issue about that, does it get complex? So is that an impediment to adoption? Yes, it is. But then, on the other hand, what else are you going to do? I mean, the situation is bad enough already with all these Heisenbugs. It's not like you don't have to fix those, and it's terrible situation to be in. So yeah, so it's an imperfect solution, but at least it's a solution. The other thing is that then verification-oriented people ask the question, well, how do you know that this model is an over-approximation of what can happen? Well, you don't know, you will not know, but some approximation, whether it's some combination of under, over, whatever, right? It's better than not doing anything at all. At least if you model it, you will have control over all the sources of non-determinism, and you'll get reproducible error traces. Yeah?
Can you repeat the question?
Sure. Okay. Yeah.
So after you make sure that the P program is fine, you translate it into
Executable C code.
right. How do you know they are equivalent?
So the question is, how do I know that the C code that is generated from P is equivalent? Well, I know it because that's done by an automated tool. You have to trust the P compiler. That was not hand done. So are you asking the question, how do I know my compiler is correct? That has become a fashionable question in the last 5 years. Before that, nobody asked this question. So I don't know. I have not tried to do any compiler verification, but that's potentially something that could be done. Yeah. Now, okay, continuing on, moving on. So now I want to give you some idea of the language and the programming model, right? So it's based on the programming model of communicating state machines. So this is the artifact manager machine. So each machine is going to have some data, right? And that data is private to that machine. So the only source of communication is by sending explicit messages, right? So those messages are going to be buffered in an input queue. So this machine receives this message M, and that goes to the back of the queue. Well, that queue was empty, so it's there. And then another message comes, M prime, that's put at the back of the queue. Now the code inside the machine is decomposed into these macro states. So here you see two states, right? Init state and reconciling, right? So these are basically blocks inside which you can put event handlers. So inside init state, it's saying that, oh, I'm not prepared to deal with the event eQuery artifacts complete. But if eStart is dequeued, then I want to make a transition to the reconciling state. Okay? So the implicit logic is that unless the event at the front of the queue is explicitly deferred in the current state, it will be dequeued and handed off to the state to deal with. In this case, let's say that the event that was dequeued was eStart, so the transition happens, and now we are in reconciling. Now the same process repeats. M prime is dequeued, and in this case, let's say it was eQuery artifacts complete. Now in this case, it says do reconcile. So this do reconcile is the name of an event handler. It's the name of a function that is written separately, and it just executes that function and stays in the state. So this is people who are familiar with the actor-oriented style of programming. So this is some kind of a mishmash of actor-style programming and state machine style programming. So it's a little bit more expressive than pure actors. Pure actors you can think of as there's a single state with installed event handlers, and you can't change the event handlers based on different states. You have to handle that using like variables, program variables. So it provides you a little bit more structure. Okay, so when it does executes the handler reconcile, it can send messages to other machines. So in this case, it sends M double prime and M triple prime to a different machine. And the same process is executing at the other machine, and the operational semantics is that, well, you get some interleaving of the execution of all these concurrently running state machines. Now, if you look at the actual code that the programmer writes inside a machine, that looks something like this. So this is some syntax here. So you specify the machine, and inside it you'll have three kinds of code segments. You will describe the data, which are the fields inside the machine, and the states and the functions. So this is what that machine looks like if you dive down into it. So you have fields. So this is declaring a bunch of variables, and you can see here that we have these types whose type definitions are not given, but you can declare tuple types and sequence types and map types, and you have primitive types like bools and ints and events and so on. Then you have a bunch of states. So here you see the code for init state and the reconciling state, and you can either write you can either give the name of a function, or you can write anonymous functions here directly if your function is very small, right? And then there's some syntax for writing down function, C-like syntax. Oh, by the way, one thing, all the, since I said C, there's no pointers here. So no heap, it's all value-based. So when you send a message from one machine to another, or if you make a function call, values get copied. Okay, so aliasing cannot occur. So this language is data race free by design, right? We do pay a performance price because variables are getting copied all over the place, and we need to work to improving the performance. But data race freedom is baked in. Okay. So now we get to, so that was the execution model and how you write environment models and the code using collection of interacting state machines. Now we look at some specification. So then first we have the baked in specifications. Like in C# you have null dereference exception, or you have the array bounds violation exception, or cast exception. So we have two baked in specifications. One of them is the unhandled event exception. So this happens when an event is dequeued and there is no handler assigned for that event in the state that the machine is in. So then this exception is thrown. Yeah.
So what is the data recipe? So let's say there are two messages to the same machine, and they share a variable. They get reordered.
Yeah. So this data race freedom is kind of a loose thing. All I was trying to say is that between machines that are concurrently running, they cannot share reference to the same object on the heap. And so you don't have to worry about that kind of low-level synchronization. That's all I meant. But of course, higher level protocol level races will happen, can happen, and that's what a lot of this testing is about. Otherwise, you wouldn't have Heisenbugs, right? Yeah, because of reordering and so on. Okay, so unhandled event exception and illegal cast exception. So the programmer doesn't have to write anything, any extra thing to get these specifications, right? So this is nice. A lot of bugs get caught this way. Then of course the programmer can write local assertions. These assertions refer to variables of a single machine, the local variables inside a function, or the fields of a machine. But the programmer, often may want to write global assertions, or general safety properties that may try to correlate the state of multiple machines. So we have a mechanism for writing both safety and liveness properties. This slide was meant for a lay audience, not for experts like you who know what safety and liveness is, so I'll skip over this. So writing safety and liveness specifications in P is very easy, very simple. We basically provide monitors for safety and liveness properties. So here's a monitor. So the syntax for monitors is very similar to the syntax for machines. So you have fields, and then you have a bunch of states that have handlers for them. Unlike machines that are dynamically created, monitors are not created. If you list a bunch of monitors in your program, they're global things. They start executing from the very beginning and continue executing. You don't have to create them. Okay. And now monitors can receive messages from many different, it's a publish, subscribe kind of thing. So if a monitor subscribes to, say, events A, B, and C, whenever any machine sends an event A, B, or C, that gets funneled into the monitor also, and the monitor can make some state updates based on that event. And that's how you can capture arbitrary temporal safety properties. Then we have liveness monitors also. So we have states here also, but now you have three kinds of states. You have unannotated states, cold states, and hot states. So we have introduced this notion of cold and hot states to introduce liveness into the story. So the metaphor here is that of temperature. So the temperature of an execution, we want it to stay less than infinity. How does the temperature change? Well, every time the execution stays in a hot state, the temperature goes up by a small value. And every time the execution enters a cold state, the temperature is reset to 0. And the temperature starts out being 0. So what we are saying here is that we don't want there to be an infinite execution whose temperature hits infinity. In other words, we don't want an infinite execution in which you hit a cold state. When will the execution temperature hit infinity? If the hot state is visited infinitely often, but after a while you don't get into any cold states, right? So we're not getting any resets. So I found this particular metaphor very easy, well, relatively easy to explain to programmers, to P users. Turns out that it's also exactly the same thing as the Rabin acceptance condition, which is great because I know that this is going to be very general and it can express all omega regular properties. Okay, so we view the test problem as we view the problem of Heisenberg detection as a testing problem, as a systematic testing problem, where we view the programmed execution as an unfolding state transition graph, right? And we are looking for some execution sequence in it that leads to a violation. And the key problem that we are trying to address here is scalability of the search, because there's of course this combinatorial explosion here because of non-determinism, either local non-deterministic choice or the scheduling choice. Everybody here knows all about this, right? This is the bread and butter problem here. So I want to say a few words about some of the new ideas we have introduced in P to solve this combinatorially hard problem. So before I do that, before I tell you about the new ideas, I first want to provide you an overview of the existing techniques. This is, of course, from my perspective. There's so many other things that I will not talk about here, but I'll talk about the things that I find are the most important in this area. The most important thing is depth first search, right? Everybody starts off implementing depth first search. It is space efficient and it's implemented in many model checkers. And everybody knows this problem that it is difficult to find debugs with depth first search because if you have a very large state space, then you might get stuck exploring some piece of the state space over here, whereas the bug is over there, right? And people have known this for years. That's why they went on to explore things like iterative depth first search. So first I'll explore all executions up to length 1, then length 2, then length 3, and blah, 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 right? So that gives you some kind of a mixture between breadth first search and depth first search, right? Okay, so we have our own take on how to find debugs, right? So we do search prioritization. So here's my high-level view of what search prioritization is. If you have a very large search space, right, then search prioritization is about creating strata, divvying up the search space into these strata. So here you have two kinds of divisioning methods. One of them indicated by the black concentric circles, and the other one indicated by the dashed blue concentric circles. So B is equal to 1, B is equal to 2, 3, 4, 5, they indicate these strata. So different kinds of prioritization algorithms will provide different way of slicing up the search space. So what this slide is trying to say is that supposing this is a bug that we want to hit. So the the stratification induced by the black strategy will hit that bug in the 5th stratum, but the stratification induced by the blue strategy will hit it in the 2nd stratum. Since the cost of search for a particular stratum is proportional to the size of the stratum, we would be better off looking at this blue guy, right? So we basically want different prioritization strategies. We want a generic infrastructure, search infrastructure, to accept different prioritization strategies and execute search in the order specified by those prioritization strategies. So that's what we have with P. So now the question is, how does the programmer specify these various search prioritization strategies? So for example, let's say that this is one particular schedule, S1, right? And then this is another schedule, S2. How do I say prioritize S1 over S2? Because these things are not statically known. These are things that are generated dynamically as the program executes or unfolds, right? So that's the problem we have to solve here. So we have this notion called a delaying scheduler that I find useful for specifying search prioritization functions for concurrent programs. So let me explain what a delaying scheduler is. Yeah, I'm doing okay. All right. So a delaying scheduler is very close to a deterministic scheduler. So let's try to understand what is a deterministic scheduler. So a deterministic scheduler, a very simple example of a deterministic scheduler is a deterministic round-robin scheduler. So imagine a concurrent program with 3 processes in it, T1, T2, T3. Okay? So a deterministic scheduler keeps scheduling T1, T2, T3 repeatedly in that order. So the way, the state that this particular scheduler will have to maintain is, you can think of it as a queue, right? Initially, the queue is populated with T1 followed by T2 followed by T3. When you ask, give me the next guy to schedule, it pulls the first guy, the guy at the front of the queue, says, oh, okay, schedule T1, and then he puts him at the back. Then you can say, okay, give me the next guy to schedule. Now T2 is at the front of the queue. He pulls it out, says, okay, schedule T2, and then puts it at the back, right? So it's a very simple data structure that the deterministic scheduler can maintain to implement round-robin scheduling. Okay, so a delaying scheduler is that with a twist, with one other thing in it. This other thing is what I call a delay operation. So in addition to supplying the next process to be scheduled, it also supports a delay operation, which gives it the opportunity to change its default scheduling strategy, right? So one example of a delay operation would be that when after scheduling T1, when instead of getting the next process to schedule, if I call delay, then it'll put T2 without giving it, put it at the back of the queue. So and now we schedule T1, T2. Oh no. So we scheduled T1, then we scheduled T2, and then we did a delay operation. So that caused the scheduler to take the guy who was at the front of the queue, that was T3, and put it at the back of the queue. And now if you call next again, you will come back to T1. So we basically skipped T3. So we got T1, T2, and then T1, T2, T3, T1, T2, T3 from that point on. Okay? So now this is one choice of implementing the delay operation. You don't have to implement it like this. But regardless of what choice you use, the interesting thing about delaying schedulers is that as long as by making enough delay choices, you cycle through every process that you may get to schedule there, what would happen is that for a very large delay budget, you get to schedule you get to generate all possible schedules in the system. So now delay budget means that if you have, I didn't explain this well. So zero delay budget, so now we're going to do search over with bounded number of delays. So zero delay means I do not allow the explorer to invoke the delay operation even once. So if we do that, we'll get exactly one schedule, right? If I say, okay, you are allowed to invoke the delay operation at most once. Well, if there are n places where a delay operation can be invoked, the total number of schedules that I will generate is n, right? And if I say, oh, okay, only 2 delay operations at most, then it will become n squared. So if d is the number of delay operations, the total number of schedules that I can generate is n to the power d. And the point I was trying to make is that if d is large enough, then you will ultimately explore all the possible schedules. But of course, the order in which you generate these schedules, if you do prioritize search, first you generate schedules with delay 0, then with 1, and so on, would be influenced by the specific implementation of the delay operation. And that's how you specify the prioritization function for the search. So once you have a particular delaying scheduler, then you can basically do this kind of stratified search. So you first generate the execution with delay 0, and then you systematically generate from it all the executions with delay 1, and then delay 2, and so on. And this was the L to the power dB is this complexity measure that I was alluding to earlier. So now the trick is that if the programmer somehow wants to search with respect to a particular prioritization function, then if the prioritization function exhibits the bug in a low value of the budget, then we'll be more efficient than otherwise. So one other point I want to make here is that this way of looking at doing stratified search, this can be combined with another algorithmic trick of sampling executions. So when faced with combinatorially large state spaces, sampling executions is a good way to search in the presence of limited time budget. The problem is that if you do a completely deterministic search, then within a time budget you terminate the search at some arbitrary point. Whereas if you do random sampling, then each sample is independent. It can be parallelized, and you get it somehow feels more like a breadth first search within a certain time budget. So that's why random sampling has proven to be very popular in dealing with these large state spaces of concurrent programs. So the classic way in which random sampling is done is just a pure random walk. So you start with the initial state, right? And then you choose one outgoing transition randomly, and then so on and so forth. So this very simple algorithm is perhaps the most popular algorithm these days for researchers, for tools that are trying to do systematic concurrency testing, because it has many nice properties. The most important property is that regardless of the bug, every execution has a non-zero probability of discovering that bug. Very elementary, right? Second thing is it's trivial to implement. It is highly parallelizable, and it doesn't get stuck anywhere, unlike any kind of prioritized search algorithm, right? If you use any kind of prioritization or depth first search, you can and you know that you're going to have to hit timeout after a certain point, you run the risk of getting stuck somewhere. This thing is not going to get stuck anywhere, right? So we can use sampling together with the prioritization. It's very easy to combine it. Basically, we lift this idea of random walk over the state transition graph to a random walk over the induced graph over the strata. So we start with the execution with no delays, and then we pick randomly one place to delay, and we generate that execution. Then from that execution, we randomly select one other place to delay, and we generate the next execution. So this also has nice mathematical properties. So if you have a bug that can be manifested in an execution with dB delays, then every execution, randomly sampled execution, will have a probability of hitting that bug that is at least 1 over L to the power dB. So that's also nice. Okay, so I'm at the end of my talk, I'm going to have 2 more slides now telling you about the work that I'm currently trying to do to improve P and some new projects that I'm doing. But I want to first see if you have any questions before I get onto that, about the current material.
Thank you so much, and I would propose that we pass around the microphone to make sure that the questions are being recorded. Are there any questions at this point?
Yeah, I have a question about the syntax. So I've watched programmers using a similar mechanism for communicating finite state machines, and one of the questions that pops up fairly soon is, do you have hierarchy, like hierarchical states? For example, if there's an error message that may arrive in any state and should always lead to a transition to the same error state, then as far as I could tell from your syntax, you have to write that again in every state clause. Is there some syntactic sugar or something?
So there's 2 kinds of hierarchy. One of them is, of course, we have functions. So you can reuse some piece of code and call it from many places. But we also have, when you make a transition from one state to another, that's the regular transition, like the go-to, right? But you also have a push transition. So if you make a push transition from one state to another, the new state, instead of erasing the current state, it is actually pushed on top of it. So you have a stack of states also. So what that allows you to do is, if you want to start some kind of a conversation with some outside thing that is going to cycle through a few, send back and forth some messages. And you do all that and you want to come back and resume from where you left off, you can do that. And if during that time you want to continue to execute some default handlers, you can do that too. There's a mechanism for inheriting the handlers that were installed at lower levels in your state stack at the top level. So you can continue to be responsive to some basic things over there.
Thanks.
How do you do cycle detection for liveness?
You cache states. You cache states and you detect a lasso.
And there are no problems with like log variables that just keep on growing or something like this? Like
yes, I mean, you can. The thing is that this thing, in general, P programs do not have finite state spaces for a variety of things. A couple things help us. One of them is that you're always testing with respect to unit tests. So the advice I give to programmers is that in your unit test, you should only create a small test harness where you create a bounded amount of work items that you are pushing into your system, right? And that by itself is no guarantee that you will not have. You can still have an integer that just keeps incrementing, but that tends not to happen. So I think that there's a good chance that just detecting a lasso is good enough, right? Another thing is that, P is a DSL. And the expectation is always that you're writing the protocol part of your software inside P, and you leave the other part that is not relevant to the protocol in C. So a lot of that kind of nonsense that you might be thinking about, right, gets smashed over there, and then the model code that you write to model all that doesn't even have all those funny variables in there. So that also helps. Yeah.
Any further questions regarding this first part of Shaz's talk? Susanna?
So now I'm a bit curious about your C. You say the C, you leave it aside. So in fact, if you detect a lasso, you don't even know whether it's a lasso.
No, you don't. I mean, it's a lasso.
It's a lasso in the model, but it's not necessarily a lasso because the C...
No, that's not true. So what's happening is that there's 2 parts to the P program. The part that is what I call real, and the part that I call model. The real part is the part that is going to be compiled to executable code. And the model part is the part that is going to be erased by the compiler. So the lasso is in the interaction of these 2 things. So, okay.
Okay, no, I thought you would leave the C part, I mean the actual C part, the variables, you would not consider them in the state, but you do consider them in the state.
That's right. For the part that is going to be compiled into C, I will consider them.
Of course.
Any more questions at this point? Okay, then I would ask Shaz to conclude his
So
talk.
I'll continue, yeah. So I just wanted to conclude by telling you about a couple of technical thrusts that we are pursuing right now in the context of P. So one of them has to do with compositional reasoning. The P language, the way I described it to you, is basically a flat collection of state machines. That is good, right? You get some benefits from all that. But I don't think it is good enough because there is no modularity here. A single state machine is not a good module, in my opinion, for reuse, for implementing a library mechanism, and above all, for doing some kind of compositional testing. So we are inspired to think about a module system for P, similar to module systems in languages like ML or Haskell and things like that, right? Where you can both provide code reuse and you can provide separate testing and verification for more scalability. So we started thinking about that when we were trying to use P to implement a large distributed system. So we wanted to build at the top layer distributed services such as transaction commit or replicated data structures, hash tables or list. And so we know that to do that in a distributed context, you have to solve some hard problems such as consensus. And there's many algorithms out there for implementing consensus. So for example, you can use the multi-Paxos suite of protocols, or you can use the chain replication suite of protocols, and there are two alternatives. And all these things would be built on top of operating systems and networking services. So first of all, what I would like to do is in my software stack, I would like to be able to implement each layer separately and test it or verify it against an abstraction of the other layers, right? The second thing is that I want to be able to do reuse. So I want, for example, this guy over here, which is solving the consensus problem, to provide the same interface as this guy, which is solving the same problem. So I can take either one of these upper clients and link it against any one of them without having to rewrite this code here, right? So So we are trying to come up with a module system that will have all these desirable features. It's work in progress right now, making some progress there. Okay, another thing I want to do is make a plug for a project, an ongoing project at MSR. So MSR Labs is headed by Jeanette Wing, who came to Microsoft from NSF. While at NSF, she started this business about expeditions, which were supposed to be, big projects that are chasing some kind of a dream and typically lots of money thrown into the pot. So she decided that, okay, well, we should have some expeditions inside MSR also, and that turned out to be really good. I think it got researchers really kicked about it because it was an opportunity to really collaborate with other researchers beyond the confines of a single conference paper, which is a typical mode of operation, right, in the research community. So we are currently doing this expedition on safe cyber-physical systems, and that's our mantra over there, towards safe autonomy in the physical world at scale. And I'm really pumped about this project. So I'm involved in this, and I'm hoping that language frameworks such as P and a lot of the verification technologies that you guys have worked in and I've worked in over the years would be useful in building a reliable software stack for building safe cyber-physical systems. We have many researchers collaborating across disciplines, including programming languages, program verification, but also systems, robotics, vision, and machine learning. So I hope that, in a couple of years we'll have something good to show you. Okay, that's it.
And let's thank Shaz. Any more questions?
Okay, thanks. So, Shaz, this is about the last bit of your talk where you spoke about the compositional methods. So, piqued my interest. So, does this mean that you are going to you have to think also about refinement and,
Yes.
strategies for testing refinement? Is that something?
Yeah,
that you're
we'll have
looking
to,
at?
basically, I didn't get into the details of it, but I feel that the only way to get compositional testing, if I want compositional testing out of my module system, then I also have to introduce a notion of compositional refinement. Because if I'm going to use an abstraction of the environment to test the service, then it would be nice if I could also test that abstraction holds on the real implementation of the environment. And that's where you have to test refinement also. Yeah, that's right.
This is what I was thinking of. Yeah. Okay, thanks.
Any more questions? One thing that struck me was when you talked about the delaying scheduler in essence to control the search, right? Have you looked into using search heuristics and heuristics
Like A-star and all that?
For instance, best first.
No, I haven't really. I briefly looked at A-star, but it also seemed to me that A-star is also parameterized in the same way. You have to supply some kind of a cost function or something, right?
Heuristics estimate function, yes, right.
So what I realized is that in order to really make this fly, you can't just tell the programmer, okay, come up with some heuristic. You have to provide some intellectual scaffolding for the programmer to think about how he should experiment with these different heuristics.
Yes.
And that scaffolding has to be domain specific. So I think that this delaying scheduler business is domain specific intellectual scaffolding. This is one way in which I think about it that I find helpful. And I wrote, my collaborators and we wrote a bunch of different delaying schedulers, and they turn out to have different kinds of properties, different kind of coverage things in there. And so it's kind of like that. It's it's a little bit like language design, I would say.
Okay.
Yeah.
Any more questions? There's one in the back. Dragan.
Would it pay off to use reduction techniques like symmetry partial reduction in your search?
So I don't know about. I don't know how much symmetry would. Maybe it would help if there's many, like in that extend nodes, right? If there's a separate process for each extend node, maybe it would help. But I'm kind of skeptical. But for partial order reduction, I didn't mention it, but there's some baked in thing that looks like partial order reduction in P. So the semantics of P are such that it's okay if you don't, so you don't have to put a scheduling point before every access to a local variable or to a field inside a machine, right? That's because, so we know it's okay to only introduce scheduling points at sends and receives, right? That's a very trivial kind of partial order reduction. But you can do something even more. You don't have to put a scheduling point after a receive, for example, even though it is dequeuing and changing the state of a buffer to which other parties can write. And that's because a receive in P semantics is a right mover. Does right mover make any? Okay, you know about right movers, yes. So we do that optimization too, but these are all, I would say, you can think of it as static partial order reduction. So at a top level, you make an assessment of whether this action is a commuting action or not. And you don't try to take these decisions dynamically, which I think is an attribute or a hallmark of partial order reduction techniques explored in the community. So we don't have that. Yeah, maybe it will help, but I find partial order reduction very challenging to think about. Yeah.
Also very effective.
That too. I'm sure.
Any more questions? Susanne.
About your observers, did you find sufficient, because we are in the past we have defined our own P language one time, which we called IF, but I mean it's very similar in a sense, but in fact we came across a problem. Did you find sufficient to have a property defined by a single monitor? Because we came across, in fact, the monitors have different composition semantics in general, otherwise you can delay the monitor and you will not detect your properties, so you need special semantics. But then you want to write your properties as compositions of monitors. So very quickly you will see if you write a single monitor, your monitors will blow up. So you will want to write them as compositions of monitors, and there you need a special semantics for your monitor. Did you come across that problem or not? I mean, we quickly came across
not really.
that.
So why does the monitor blow up?
Because in fact, because of a partial order explosion. Because if your property is kind of an ordering, some orderings are okay, and some orderings are not, very quickly you come to such kind of things.
So yeah, I see what you mean. Yeah, because in monitors, unlike in the real program, you can combat some of that combinatorial explosion by deferring events. In a monitor, you can't defer events, you have to handle it, right? Yeah, no, so we haven't, but maybe it's just because we haven't looked at very complicated things.
Yeah. If you only look at simple invariants, of course, you will not come across. We quickly came across.
Can you give me an example of a property that has a problem?
It's a long time ago. You allow certain orderings and you don't allow certain orderings. Very quickly you want to write your monitor as a kind of synchronous composition or partially synchronizing composition of monitors. You need kind of special semantics of these monitors. You want to synchronize on events. You want that a event drives several monitors and that the monitors synchronize amongst them. And then you come into the problem that you have to verify that you verify the right property.
So what happened with IF?
Yeah.
So what?
It's a little bit, we have to revive it.
Okay. All right. I would really like to understand more about what was your experience behind it. Did you get people to use it? If they used it, what was their experience? If you couldn't convince them, why not? Things like that. Yeah.
Okay, so let's thank Shaz again for this very interesting presentation. And on behalf of ETAPS, I would also like to hand over this little gift to you in appreciation for your talk. Thank you very much, Shaz.